So today I'm going to be talking about just giving you a very, very basic introduction to what Python is, what the notebook architecture is, which you would be utilizing throughout the duration of this course. My name is Maria Vincent. As I introduced myself earlier, I'm a graduate student at the Institute for Astronomy. So this generally falls. So for those who have checked out last year's tutorials on the course website and GitHub, it follows the general structure of the course of this tutorial, which was taught by Chetan last year. So yeah, here it goes. So what exactly is Python? To put it simply, it's an object-oriented programming language, which is quite easy and very beginner-friendly compared to a lot of other programming languages out there. Compared to C++, IDEO, Java, which is not very intuitive. Python is Python because of its quite simple syntax, because of how very closely it relates to just regular English sentences. Like if you want to display something, you would just say print so and so. If you want to add something, you would just do the number plus the other number, or the variable plus the other variable. So it is very easy to understand because of its simple syntax. It's beginner friendly. And there are a lot of resources available. There's a lot of open source software modules and packages suited for various scientific and data purposes, which is why it's very popular. It can be used for data analysis, machine learning, to develop websites, to develop these automated scripts that just runs through rows and rows and rows of numbers. It can be used. Python's also used to create prototypes of softwares and to test it, and just for general everyday tasks, just to make some amount of processing and system operations a little easier. And fun fact is that it got its name from Monty Python's Flying Circus, just because the creator really liked the show and he wanted a name that was short, something mysterious that would immediately strike a chord with its users. So Anaconda, Miniconda, from the many emails and messages on the course Piazza. So let's start from the basic. Conda is an open source package management system and environmental management system. What that means is it is basically this huge sack that contains a lot of different elements of creating and creating and distributing software. It was primarily created for Python, but you can also use it for pretty much any language. Most people use it for Python and R. It lets you sort of shift between different programming environments. And by that what I mean is within your so you can think about it as like within a little city. You're creating these different buildings for different purposes. Within a city, you have a school for teaching, you have a hospital that takes care of the sick, you have a building for people to live in. In the same way, within Conda, you can create different environments that all have the same base way of operating, except that you might have some slight differences maybe between Python versions. Maybe you want one environment that has an older version of Python because some software can run only on an older version of Python. In another environment, you have a newer version of Python plus some extra modules because it operates differently. Then maybe you can have an environment just for astronomy because you have all the astronomy-related packages. Now, what are packages? What are modules? You'll be slowly learning that over the course of the next few weeks. So I'm not going to dive into that real quick. But what you need to understand is just that Conda is very important because that's how you create your various environments. You manage your environments, and you can also install the open source packages that you need to write or run a Python program. Anaconda is a single distribution system. It basically is, so you have Anaconda and Miniconda. I'll explain the difference between the two. Anaconda is a single distribution system. It already comes with a lot of scientific packages installed for basic scientific data analysis. So you don't have to install them separately. You still have to install a few that you need specifically for your field. For some astronomy modules, they don't come pre-packaged with Anaconda, so you have to install them separately, but most things do. And as I mentioned earlier, even in Anaconda, you can create these different environments to run Python differently or to add different packages to each. Miniconda is a much more minimalized, much more simple installer for Anaconda. So Anaconda comes pre-packaged with many things. Miniconda does not. It's just, if Anaconda is a mansion, Miniconda is just a little cottage, basically. It doesn't come with all packages. You can certainly install them later. So I guess the pros and cons of Anaconda and Miniconda is mostly about storage. If you have enough storage and you don't want to install things separately, just go ahead, install Anaconda. But if you have very limited storage and you just need certain packages at different points of time and you're not sure which, Miniconda is a good place to start. So I think for the purpose of this course, Miniconda is also fine. You can just go on installing the packages along the way as and when you realize you need them. So I've been mentioning these things: functions, modules, packages. So these are just very fancy words for things that you'll be using on Python, which I would give you a short preview of. But before that, you should also know how to use Python. How do we write commands? How do we write a script for automating some process? So you can use Python on terminal or command line. So as Chetan mentioned earlier, you have these many commands to navigate between your system. You have these commands to create files, delete things. In the same way, you can use that same platform to even write Python programs, and not just for Python. It is also true for other languages, but here we'll be focusing on Python. So you could use terminal or command line if it's Windows. You could use text editors and scripts, or you could use notebooks. I'm going to show you how each of these work. So in a terminal or command line, it's basically line by line programming, meaning you write this one line of code, you run it, and then you go to the next line. You cannot just write a bunch of code together and run it all together. But the best part of terminal command line is you can see what's happening in real time. You can import things, you can import or install modules. What are modules? Are basically this sort of library of many subcommands that you would need, and the library usually represents one whole function. So for example, as an example of line by line programming, you can see this terminal window over here. It's basically, so over here I've just taken two variables A and B, and then I add them together, and I print the result. Print A plus B is equal to whatever A plus B is. So because A and B was 3 and 5, A plus B is equal to 8. So you see I've imported something called NumPy. NumPy here is a module. It basically has a lot of mathematical operations. So I import it to use functions within NumPy. So a function within NumPy is linspace, as you can see here. Linspace basically creates arrays of numbers for you. If you define the starting point, stopping point, and how many elements between that starting and stopping points. So you can import modules. You can also install them. So over here, I've tried installing a module called matplotlib. As you might infer, it's basically a plotting library. It has a bunch of functions that let you create plots and modify those plots. But I already have this module with me because I have Anaconda, and also it's a very, very basic module. And that's why I have this requirement already satisfied message, multiple of them actually. And yeah, so that's kind of one way to check if I have the module or not. But if I did not have the module, then you'll see a bunch of messages that shows how the module is being installed. So that's about using terminal or command line. The next way is using text editors, and these are kind of similar in the sense that you again write different lines of code. You can write all the functions that you need, but then you would run it together as a script. So syntactically speaking, the reason I wrote syntax in the title is to emphasize that syntactically it's basically the same as running it on terminal or command line. But instead of line by line programming, it is a script programming, meaning you're just going to write a bunch of lines of code, save it as a script, which is a .py file, and then you can run it. So you have something, you can use basic text editors like TextEdit on Mac or Notepad on Windows, or you could use Sublime, which is a slightly advanced text editor. The advantage being it actually color codes the syntax. So you could see, so like a function would be a different color from an input, and then a number would be a different color from string input, like that. So you could create, but you could also use Notepad. So right over here, if you see, I created this file called sample_plot.py, where it's just bunch of code. It's not color coded, it's simple, but you save it as .py. Then you go to your terminal or command line and you type Python, or if you want to first move to the directory in which your file is saved. So I saved it on my desktop. So I follow CD desktop, and because I start from my main root directory, I go CD desktop, and then I type in Python, the name of the .py file with the extension. And when I run it, I get that plot. So I did plt.plot. So I imported this module with the submodule as plt. I plot it and I show it, and as a result, I get this figure right here. So this is using a text editor. But there are also script editors that are script editors like Visual Studio Code and Spider, which are basically these coding environments. You could write code there, you could write your script there, and within that you can actually run it and you can see your results. So after going through this, I will quickly show you that very shortly. So this is about using text editors and script editors, I guess. So this is what Spider would look like. You basically write your code, and then you can you have the option of running the whole thing, and you can see the results. So I print hello world, which is the very standard basic thing that you do when you first learn programming. And then I do multiplication over here, and I get what the product of these two numbers is. But you could also use it to display a plot, which I'll show you shortly. And if I had a plot, I could see it over here. And then there's this option, Variable Explorer, that lets me see what variables I have created and what's there in my memory, how much space it's taking in memory, etc. So now Python notebooks. Now, what is a notebook? It is kind of like a regular notebook where you can write things, you can draw things, you could do a bunch of stuff with your notebook, right? So a notebook is a much more flexible, much more interactive version rather than simply writing your code on a text editor. You could write a small portion of code along with rich text. By rich text, I mean text with formatting and images. The tutorial is written in Jupyter Notebook, so you can see how well formatted it is. Jupyter Notebook is the default Python notebook format. That Jupyter Notebook architecture has also been used for some cloud-based options, Jupyter Lab and Google Colab. Jupyter Lab is also hosted. It was also Anaconda thing. Google Colab, as the name suggests, it's like coding on a Google Drive. Okay, so the Python tutorial was written in a Jupyter Notebook. That demonstrates why, and I will show you quickly, and you will better understand why a notebook environment is preferred to writing your code on terminal or a script editor, and how it being interactive makes your experience so much easier and so much fun. So a quick introduction on what software and data carpentry is. It is a very, very helpful website which has a bunch of resources that is put together by volunteer instructors from universities and just independent groups all around the world. They have amazing exercises and tutorials to get you familiar with not just Python, but most programming languages that you need, including like the super new ones that have come up. And so they have exercises, tutorials, and you can also see announcements for various workshops over there, which teach you very specific computing skills. And you can pick and choose based on what your field of research would demand from you. So let's go to the Python tutorial. So this is a tutorial I've designed for you. I've begun it with some, really short answers to all these questions and the things that I discussed in the slides, with screenshots of what things look like. So yes, I would first show you how Spider looks. Let's see. Okay, you can see it here. So basically, as I said, you can create Spider is a Python script environment where you can write script and you can run the whole thing without having to go to terminal to run it. You could see the results right there. So you could create plots, you could see your plots, and in the console you could see the other text output. And whatever error messages you get, because I made a mistake by not importing NumPy first, which I later corrected. You could see my error there. So you can see all your outputs, and it's actually beautifully designed. Visual Studio Code also works the same way. Or because this is a .py file, I can, if I don't want it to be this fancy, I can just go to terminal and run it. So this tutorial, as I mentioned, has been written in a Jupyter Notebook. Well, I'm running Jupyter Lab right now just because I like it a little better. But the architecture is essentially the same. So this is a basic. This is just for you to visualize how Jupyter Notebook, how the whole notebook thing works, and to get you acclimatized to this environment, because this is what you'll be using very shortly. So you can, instead of having to run all lines of code together as a script, a notebook enables you to break your code into these little chunks called cells. So in this script, as you can see, I had to run this first part before running the second part, even though this first part over here has nothing to do with my plot, because my plot is an entirely different set of data. The things before that is an entirely different thing. But here in the notebook architecture, because we're breaking things up into different cells, I can pick and choose what cells I want to run. I don't need to run the whole thing to get to the last bit. I can run this, and then I come back to this. So let's do that. So first I import these libraries that I need, numpy and matplotlib.pyplot. What are these? Why I have written it, import something as something else, is basically I'm aliasing it. I don't want to write these big words over and over again, so I just write these little, just few letters. And referring to numpy as np and pyplot as plt, it's a very standard way of aliasing it. You will learn more about this next week. So shift and enter, I can run the cell, and for some reason it's taking a while. Okay, it did. And I can skip this if I want, because as I said, it's not relevant. So I'm just going to go to the plot. And so as you can see, you have these texts that I've written following a pound sign. These are comments, and it's very, very highly recommended to do so for whatever piece of code you write. Because when you're writing code, you could imagine you're writing something for someone else to see, not just you. So you don't want to forget. You don't want to be the only person who can read your code. You want to be able to share and distribute code eventually, because that's how open software works. That's how writing pipelines work. So you would essentially want to write comments. You could write one-line comments by putting a pound sign and then writing whatever you want, or you could enclose comments in triple quotes like this. So this is to create a very basic plot, and there you go. Now, this is something very basic. I can also read in data from an external file and plot that. So in astronomy, especially for those interested in observing, whenever you observe, you observe something on the sky and you save the data from your telescope, and then there's like a bunch of processing it should go through. The final result, even the observed data, is saved as something called a .fits file. .fits is the extension. So to whatever operation you need to do with that, you need to have the separate astronomy package. So astropy.io is a very, very important astronomy package. And from that, I import this module called fits. And now I can read my data using fits.getData from this image that I've saved in this directory. The writing what my directory name is, it follows the same Unix way of defining your directory, your subdirectory. So I'm going to run this cell. Oh, sorry. But now you see I get this error because I forgot to import my module. So now I run these, and now I can, so you don't need to exactly understand, I understand this might be a little overwhelming, but all you need to know is that this image is basically a giant matrix. It is a 201 by 201 matrix of data points. So which is like what, over 40,000 data points, each having a certain value. What the value of the data point is, it will typically be given by this thing over here. And I can technically adjust what my contrast limits are, so I can actually see what my data point is. Okay, this is curious. I don't know why it's doing this. It certainly did not do this before.
I can see the data. It's just sparse.
Okay, yeah. So I think it's probably just me seeing it then. All right, but yeah, you can adjust contrast limits. There's a bunch of stuff you can do. You can adjust contrast limits. You can adjust how much of the data you want to see. Right now, it's just restricted to a small portion, but you could define your axis limits. You could change your axis labels. You could change the image size. You could even change the color scheme. There's a lot of different things you can do to visualize the data as much as you want, as you prefer. So this is 201 by 201 is not that large of a data set. Now, we can now, I'm going to show you how Python is actually much more powerful than this. So I'm going to read in a file that contains 20,000 rows of data distributed between 97 different columns. So that's 20,000 by 97. So that's like what? 2 times, yeah, that's like a lot. 2 times 10 to the 6 data points, 2 million data points. There you go. So I'm gonna read in all of that and then use 2 columns to create a scatter plot. And this you might have actually seen in the 2021 version of the tutorial if you've explored it. So this is another very, very useful library module called pandas, which is used to import and read in different files. So there's a .csv file which gives you the 20,000 closest stars from the Gaia archive, the DR2 version. The DR3 version is just come out. And so you can see how quickly that was plotted. There's like a huge bunch of data points that I plotted just like that. It might be a tiny bit faster. My computer is definitely slow. So again, you can change how you want to visualize this. You can change the size of your scatter points. You could change the colors. You could read in more data. And this is just 2 columns. I could also read in 3 columns and make this a 3D plot, which you're free to explore at your own time. So the whole point of this exercise was just to show how versatile Python is, how much data it can read in so little time, and why it is a very, very handy tool to use, and why every astronomer should know how to use Python. And as I mentioned earlier, here's a link to the software and data carpentry for Python, which should give you a good idea and has a bunch of exercises to get you familiarized with the language and the environment in which you'll be working with the language. So that's all I have, and this is your assignment. I would advise you to go through this tutorial and repeat all of it on Google Colab, so it's a different environment from what I used. Make sure you understand it, and you can feel free to add your own comments along the way to explain to yourself what you've been doing. Commenting is a very useful skill because sometimes you write code and then you come back to it like 5 years later, you should be able to understand what you wrote. Now, another thing that's important is you should be able to save these images, because what's the point of creating plots that are useful but you don't save them? And taking screenshots is not viable because the plot that's displayed in your notebook is not of a very high definition. So for saving, go to the tutorial on software carpentry and then save the plots that you create there. And the third optional exercise that I think is fun is to print the Fibonacci sequence, which I hope you know what the Fibonacci sequence is. And I've also given a hint here, use a for loop. What is a for loop? Again, there are tutorials, there's Stack Overflow. Google's your best friend when it comes to coding. And again, comment your code. So yeah, this will be uploaded on GitHub. This resource is available for you, and you feel free to ask questions, and the moderators are there to help you out. Thank you.